Hello everyone, in this talk I'm going to describe a novel data structure for load-aware traffic splitting in programmable data plane. To meet performance demand of modern applications, network operators typically provisions high bandwidth by exploiting multiple paths in the network. For example, the capacity across paths is used to serve traffic between toll switches in data center networks and between data center sites in private wide area networks. To achieve good performance, we need an efficient load balancing strategy. In particular, traffic splitting should quickly adapt to traffic conditions such as link failures or bursty workloads. Take this network topology for example. When there is no traffic from source 2 to destination, we must split traffic from source 1 to destination equally between the two paths, so that we can efficiently use the available bandwidth. On the other hand, when there is some traffic from source 2 to destination, we may want to split the traffic from source 1 to destination unequally. Notice that the workload is dynamic, so the traffic condition can change very fast, and therefore, the traffic splitting decisions should not only adapt to traffic condition, but also adapt to it very quickly. Let's see some existing approaches. There are two classes of load-aware traffic splitting solutions. In one class of solutions, all decisions are made entirely in the data plane, such as Hula and Kanga. Take Hula for example. It periodically sends probes from destination node to source node, and along the path, the probes will collect the performance matrix and update the forwarding table accordingly, so that the source node can send the traffic along the best path. However, this may overload the best path, especially when round-trip time is large. Another line of work is split traffic over multiple paths instead of a single path. They also collect traffic conditions using mechanisms like probes, but they assign path weights so that more traffic can go through paths with less congestion. However, even though these solutions can split traffic across multiple paths at the same time, a control plane solution is too slow to adapt to network conditions, and it is unclear how they can work in today's commodity data planes. In this work, we bridge the gap between these two classes of solutions by addressing the question of how to balance the load across multiple paths entirely in data plane. So we propose new data structures which enable load-aware traffic splitting in data plane, and study the trade-offs of these data structures. We finally propose a data structure dash which can work quite well across many scenarios. There are mainly two key functionalities that a traffic splitting data structure must support. First, when the traffic packet comes in, we need to spread the flow across multiple paths according to the data structure. Second, when the probe comes in, we need to update the data structure according to the load status in the network. Fortunately, the emerging programmable switches like P4 switches allow us to implement such data structures in data plane. In P4 pipeline, there are several match action stages, and each stage has its own registers. We can design each stage to process the packets as we want, but there are some constraints. First, when the packet arrives at one stage, it can only access a limited number of registers. Second, when the packet moves on, it cannot access the register in the previous stages. Finally, because of the hardware limitation, the algorithm on the switches cannot be too complicated. Now we know the constraints. Next, I will show you some strawman solutions and how they violate those constraints. To understand the strawman solutions, first we need to know one existing technique for weighted traffic splitting, WCMP. The idea is to replicate the table entries with the same path ID so that the number of entries for each path is in proportion to its weight. With this table, we can spread the packets across multiple paths as desired. However, updating the WCMP table as probes arrive in a short time is very challenging. One idea is to iterate over the table, and for each path, we allocate the corresponding number of entries in proportion to the desired weight. But in order to update every entry in the table, we need many accesses to the registers. Given the aforementioned constraint, it is very difficult, if not impossible, to do this with one single probe packet, especially when the table size is large. Another alternative is to divide the required updates to the table across multiple packets. In our paper, we show a way to keep track of the number of entries for path, so we can update the table more accurately. I won't cover the details, but notice to support this, we need to sequentially read multiple registers across multiple stages, and then write to the earlier register again in a later stage. Since the read-write to the same registers from different stages cannot be supported, it would require packet recirculation, and therefore it is inefficient. Finally, our proposal dash works very differently from WCMP-based algorithms. Instead of replicating table entries, dash partitions the hash space into unique regions and assign one region to each path. For example, assume we have 3 paths and their corresponding weights. The hash space is divided into 3 regions, where the region size is in proportion to path weights. And dash will only store the boundaries between these regions in the registers. So when a packet arrives, dash is able to determine the region the hash value matches, and therefore the corresponding path the packet should be forwarded to. Updating boundaries in dash is relatively simple compared to that in WCMP-based algorithms. All we have to do is to calculate the boundaries by accumulating the weights one stage after the other. For example, we have 3 paths with weights 3, 2, and 1. Dash will calculate the first boundary by adding the first weight 3 to 0, and then the second boundary by adding the second weight 2 to the first boundary 3. And we can get the third boundary in a similar way. All this can be done during the process of the probe packet, because we only need to access one register per stage, and we do read and write to the same register in the same stage. Dash is both fast and efficient. We built a prototype of dash in NS3 simulation. In this talk, I will show you one set of experiments. You can find more interesting comparisons in our paper. We used symmetric fat tree and ran different network load. We measure flow computation time as performance metric, so lower is better. We have 3 baselines. First, it's control plane solution, which can only adapt to the network conditions very slowly. Second, it's Hula, which can adapt to the network condition very fast, but can only use one path at a time. Third is ECMP, which can split the traffic across multiple paths, but cannot adapt to network conditions. And our solution, dash, can exploit multiple paths and adapt to network conditions fast. So dash can outperform all the others. In conclusion, we propose a data structure which enables adaptive weighted traffic splitting entirely in data planes. This data structure, dash, is fast and efficient compared to other strawman solutions. As future work, we will implement dash in commodity switches to show its feasibility and build a distributed traffic engineering system by integrating dash with other weight updating algorithms in data plane, so that we can address the traffic dynamics in modern networks. I conclude this talk with this slide, and thank you for your attention.